So for this part, we'll be talking about subspaces, section 4.2. So earlier this morning, we discussed what we call vector space. So for example, suppose this is our set vector space. Okay, this is our vector space V with the defined operation. Okay, so vector space, and this vector space has several elements. Okay, and we call them vectors. So suppose this is our vectors. Okay, and of course, as I have said, this vector space is not empty. It has at least one element. Okay, the zero vector. Okay, so what is a vector space, or what is a subspace of a vector space? So if we are looking at this vector space, what we can do is to collect some elements in the vector space. Okay, so suppose this is that set. Okay, so this is a set W. So let me just label this set W, and its elements are just elements from the vector space V. Okay, so the natural question is this set W a collection of elements in this vector space V? Is this also a vector space? Is it possible that we get a collection of vectors in the vector space, and that collection becomes a vector space in itself? Or is it possible that if we get a collection of vectors in the vector space, is that set not a vector space? So we want to answer those questions. So what is a subspace? So subspace is actually a vector space in the original vector space. Meaning, you have the vector space V. You get a collection of vectors. Okay? Label it W. It is a set. Okay? It is a set. And then suppose this set inherits the operations of the vector space. Meaning, you define also the addition. Okay? You define also the addition and scalar multiplication in the set W. If that set W is also a vector space with the addition and scalar multiplication attached to it, then we say that W is a subspace of the vector space V. Okay? So let us define this properly. A non-empty subset W of a vector space V is called a subspace of V if W is itself a vector space under the addition and scalar multiplication defined on V. So we say that the addition and scalar multiplication of W, okay, were inherited from the vector space V. It is a subspace because W is simply a subset of your vector space V. So remember, subset from maybe set 4 or set 5, you are given a set, okay? You are given a set, you collect some objects in that set, the collection is a subset, okay? So in here, you have a vector space V, you get a collection of objects in the vector space V, and if the collection becomes a vector space itself, then that collection becomes a subspace of V. Okay? By notation, our notation will be this. So W, it looks like less than or equal to V, but this is actually read in terms of vector spaces. This is actually read as W is a subspace of V. Okay? Remember, maybe you have the notation that looks something like this. Okay? So here you say that A is a subset subset of V. Okay? So for this notation here, W is a subspace of the vector space V. Okay? And again, since W is itself a vector space, okay? W is itself a vector space, it has addition and scalar multiplication. And the addition and scalar multiplication are the same operations from your bigger vector space V. Okay? So here, we have a vector space V here. Okay? Vector space. And you have your addition and also the scalar multiplication. Let me just write this scalar multiplication. Okay? And then you get a collection, okay, of objects. This is your W. So these two operations here will be inherited to that W, okay, to that set W, okay? And if W is a vector space with these operations, then W is a subspace of V, okay? Now, we want to show that W is also a vector space under the same addition and scalar multiplication defined on V. So meaning, naturally, by definition, we have to check all of this. 10 conditions for W. Okay? But the question is it necessary to check all of this? Okay? Now, notice, W is just a subset of uh, V, meaning the elements of W are also elements of V. Okay? Elements of W or objects in W are also objects in V. Okay? So, if the objects in W are also objects in V, and we are using the same addition and scalar multiplication from V, okay, it means that all the objects of W would satisfy this. Okay? All the objects of W will also satisfy this. Okay? Also, all the elements of W will satisfy this, this, and this. Okay? And also axiom number 10 here. Okay? So what does this mean? If you get a collection of vectors from the vector space V, okay, and call it W, axioms 2, 3, 7, 8, 9, 10 are trivially satisfied. So what's left to show for the set W is axiom 1. Okay, so this time we are now going to replace this with W. Okay, so if U and V are objects in W, the question is U plus V also in W. Okay, so we have to check that one. Okay, we also need to verify that the zero vector of V is also in W. Okay, so we have to verify axiom 4. Okay, we have to verify axiom 4. Not necessarily this guy. Okay, not necessarily this part. We only need to see that the zero vector of V is also in the set W. Okay? We also need to verify that if we get an object in the set W, okay, its negative is also in W. Okay? Its negative is also in W. So again, this time now we will replace this with W, and this time here we will replace this with W. So for each object in W, okay, we must find the negative of that object in W also. Okay? And finally, scalar multiplication must hold true. Okay? So this must also be checked. Okay? So again, we are now going to replace this W and also this one W. Okay? So meaning from 10 axioms, okay, if we want to prove a vector space or we want to prove a set is a subspace of the vector space, we only need to check 4 things. This guy here, this guy here, this guy here, and this guy here. Okay? Those are the four things that we need to check because 2 will be trivially correct or satisfied. 3, 7, 8, 9, and 10, they will all satisfy because again, the objects in W are just objects in the vector space V. Okay? Now, we are down to 4 objects. We are down to 4 objects or 4 axioms, sorry. We are down to 4 axioms and we want to show that these 4 axioms are satisfied by the set W. Okay? By the set W. The question is, do we really need to verify all of these 4? Okay? This theorem tells us that we only actually need to verify 2 of them. The closure under addition and the closure under multiplication, scalar multiplication. Okay? So if W is a non-empty subset of a vector space V, then W is a subspace of V if and only if the following conditions are satisfied. If U and V are vectors in W, U plus B must be in W also. Okay? If K is a scalar and U is a vector in W, then KU must also be in W. So how? Why? Why do we need to check 2 statements instead of these 4 statements? Okay, why do we need to check only 2 statements and not the 4 statements left? Look at this. Look at this. Here, 1 will answer axiom 1. Okay? 2 will answer axiom 6. Okay? So we're checked with 1, we're checked with 6. The question is, how about axioms 4 and 5? How about axioms 4 and 5? Look at this statement number 2. If K is a scalar and U is a vector, KU, or if K is a scalar and U is a vector in W, then KU is in W. Okay? Statement 2 implies the following. Let K be equal to the 0 scalar. 0 scalar. What is KU? Then KU, this is equal to the 0 vector. Okay? So what does this mean? U is a vector in W, K is any scalar, Ku must be in W. So if we take K to be the zero scalar, Ku is still in W, but Ku is now 0. So 0 will also be in W. So this implies that 0 will be in W. And this is your axiom 4. Axiom 4. Okay? How about axiom 5, the existence of negative? You can have K equals negative 1. Then Ku, this is negative U by the theorem that we had. Okay? So this implies that if U is in W, then negative U will also be in W. And this is your axiom 5. This is the axiom 5. Okay? So axiom 4 and axiom 5 will follow from statement number 2 here, which means we only need to check closure under addition and closure under scalar multiplication in the set W. Okay? So from 10 statements, we reduce it to 4 statements, but 4 and 5 will come from or will follow from statement 6. So we only need to check 1 and 6. Okay? And we call this the subspace test. Okay? So if at least one of these two is not satisfied by that non-empty subset W of the vector space V, then your subset, the chosen subset, is not a subspace. Okay? Example, let V be any vector space. Okay? That 0 vector in W, if 0 is the 0 vector in W, then this set W, okay, this set W, the set containing that 0 vector, is a subspace of V. It's the trivial subspace. Okay? So you have the vector space, you get the 0 vector there, put it in a single set, it's always a subspace. Okay? Just make sure you are defining the addition and scalar multiplication on V. Okay? So it's the trivial subspace. So in short, every vector space has at least one subspace. Okay? In fact, there are at least two subspaces. The other, we call this the improper subspace. The vector space V is a subspace of itself. Okay? It's like in the set theory, any set is a subset of itself. Okay? Any set is a subset of itself. So we can go down or we can transfer this property here in the vector space. Okay? Any vector space is a subset or is a subspace of itself. And we call this the improper subspace. Okay? Improper subspace. The smallest subspace of your vector space V is this one, the trivial subspace. Okay? So meaning, if we look at this chain, you have the 0 subspace. Okay? This 0 subspace will be a subspace of W. Okay? If this is a subspace of V. Subspace of V. Subspace of V. So here. So if W is a subspace of V, okay, then that W will have a subspace, the trivial subspace. Okay? This is the smallest subspace of a vector space. And of course, the largest subspace of a vector space V is itself. And all other subspaces will be in between the two guys here. Okay? So this is true for any vector space. For any vector space in V, we can always have these two vector spaces as subspaces of your vector space V. Okay? Example. Let V be the vector space of all real valued functions. All real valued functions. Okay? All real valued functions under the usual addition and scalar multiplication of functions. So we had this example earlier. Okay? So what we're going to do is to collect the set of all real valued continuous functions. Okay? So you have the set, you have the space, F here. Okay? You have the space F here, space of functions, real valued functions. The space of continuous functions may be somewhere here. So if you only look at the continuous functions, real valued continuous functions, it will be inside the space of functions. Okay? So if we define the usual addition and scalar multiplications of functions of on W, okay? So you have the vector space F here, or F negative infinity to plus infinity, and then you look at your W to be the space of continuous functions on R, then this W will be a subspace of V. Okay? W is a subspace of V. And for this, the proof of this, we will need your calculus 1. Okay? So we only need to prove two statements. Okay? The first statement here, sum of two continuous functions, two continuous functions is also continuous. Also continuous. Okay? From calculus 1. And then the other guy here is if K is a real number, and f of x, let's say f of x is continuous, then k times that f of x, is also continuous. So this is your statement 1. You recall from calculus 1. Okay? So these statements are all by Cal 1 concepts. Okay? By Cal 1 concepts. So the space of continuous function is a subspace of the space of all functions. Okay? So the space of continuous function is much smaller than the space of all functions, because functions, it may be continuous or discontinuous. Okay? A function may be continuous or discontinuous, but you only collect all those continuous functions. Okay? And because continuous functions, if you add them, will give you another continuous function. And if you multiply any real number to a continuous function, the resulting function is also continuous. And therefore, W is a subspace of V. Okay? Next, let V be the vector space of all ordered pairs of real numbers under the usual addition and scalar multiplication. Okay? So R2, the two space. Okay? The two space. And what do we want here? So we are defining the usual addition and scalar multiplication. That means component-wise addition and multiplication to each component for the scalar. Okay? Now, we let W to be this set. First coordinate is always 0, and X is any real number. Okay? So this guy here, this is an ordered pair. Meaning this collection W is also elements in V. Okay? Then under the same operations of V, meaning the usual addition and scalar multiplication, W is a subspace of V. Okay? And how do we prove this? Again, the two um, statements. So you will see you have 0 x1 plus 0 x2. Okay, this is equal to 0 comma x1 plus x2. And what is the condition so that you are in the set W? Your first coordinate must be 0. And look at this. 0 plus 0, it's 0. So the first coordinate is 0. So this guy here will be in W. Okay? And number 2, k times 0 times x. We know that this is just 0 comma kx. Okay? Because 0 times k, it's still 0. And the first coordinate here is 0. And that means this element here is in W. Okay? Therefore, this W here is a subspace of V. Yeah? Question on how to use the two statements to show that the collection of vectors in a vector space is also a subspace, is also a vector space. So we just need to consider the two statements. Okay? Now, how do we construct subspaces? One way is the following. Suppose we know W1, W2 until WR. Suppose we have a collection of subspaces of a vector space V. Okay? Okay? So, for example, I'll just draw this. Okay, I'll just draw this. So, for example, this is my vector space. Okay? Take note, W1, W2 until WR are all subspaces of V, meaning all of these, W1, W2, and WR contains the zero vector. Say this is your zero vector. Okay? So, maybe this is your W1, and probably this is your W2, this is your W3, okay? Okay, and let me add another one. This is W4. So let me label this. This is W1, W4, W3, and this guy here, it's W2. Okay? So we have 4 subspaces here. Okay? So this theorem tells us then their intersection is also a subspace of V. Okay? Their intersection is also a subspace of V. If we look at properly this set, the intersection is this. Okay? So this guy here. Okay. So if you look at properly, this is the intersection. Okay? Meaning all the elements in this shaded here, they are also elements from W1, W4, W3, and W2. Okay? They are all inside W1, W4, W3, and W2. Okay? This guy here, let me show you another shade here. This guy here, this guy here might not be clear to you. Okay? So this part here, the elements of this are inside W1 and W4, but outside W3, because this is your W3 here, and also outside W2. Okay? So the yellow part here is just those elements which are inside W1 and W4, but outside W3 and W2. Okay? Okay? Similarly, if you can get other collections. For example, maybe just one more example for this. Example, this guy here. Okay? So this part here, it's inside W2 and also inside W3, but outside W1 and W4. Okay? Etc. So this shaded part here, the red one, okay? The red one here, the elements in this part here are all inside W1, W4, W3, and W2. So that's the intersection of all of them. Okay? So the theorem tells us, if we know these subspaces, W1, W2, W3 until WR, you get the intersection, okay, you get the intersection, then that intersection is also a subspace of V. Okay? Yes.
So in this case, would we have to consider all the subspaces?
Yep.
So like every single one that exists in vector V, vector space V,
Nope. Not
because
that. Look at
yeah,
this. There are objects in here in V, but they are outside any of these.
then wouldn't this apply even with, let's say, two subspaces? Like that would still hold true.
If you only have two subspaces, you get the intersection of that. The
Mm-hmm.
intersection is a subspace. Okay?
Okay,
The
so
intersection is a subspace.
the number doesn't really matter. Then the
Yep.
number of subspaces.
Yep.
Okay.
Nope. Okay? So if I am going again, um, so look at this. This yellow part here, W1 and W4. This guy here, it's also a subspace. This guy here, this yellow part, this yellow part, it's not a subspace. Why? Look at the zero vector. It's inside the red, but outside the yellow. Okay? You get that? Okay?
Yeah, I get that.
Yep.
Like here we have four subspaces,
Yep.
so the intersection of all of them would be the
The
yeah
will also be a
part of
subspace.
V.
Yeah.
Uh,
Okay.
so it really depends on how many they give you, kind of, how many
Mm,
subspaces are given. Or
let us look at another one.
yeah,
Let us look
sorry.
at another one. Suppose you have this. You have the vector space V here. Okay. You have the zero. This is your W1 and this is your W2. Your zero vector. So this is W2. Your zero vector is somewhere here. This is your zero vector. This intersection here will be a subspace. That good?
Yeah.
Okay. I get another subspace. Okay. Suppose I get another subspace. This subspace here. Before I get this, okay, before I get that, so this intersection here, it's a subspace. Okay. This intersection here is a subspace. I get another subspace. Because it's a subspace, it contains the zero.
So it, if you look at it another way, the subspace inside the intersection would be a subspace that would hold true for the outside subspaces. Okay.
I
That
didn't
make
get that.
uh I'll think about it. So
Okay. So anyway, so try to think about it. So again, I started with the two subspaces, W1 and W2. And you have the shaded, the blue shade. Okay. I get another subspace W3. Okay. Now I have another subspace. This guy here. That's another subspace. Okay. I get another subspace. Okay. I get another subspace. Something like that. Okay. W4. So you see, this is another subspace. This guy here. Okay. So every time you get another subspace to intersect with your previous intersection, the intersection becomes smaller and smaller, possibly. Unless this is your case. You have a subspace V here, okay? You have you have a vector space V there. You have a subspace W1 here and then another subspace W2 here. Okay? The zero vector is somewhere here, somewhere there. Yeah, it's somewhere inside. Must be somewhere inside. So anyway, I'll have this. Your zero vector is somewhere inside that. Okay? Then their intersection becomes just this guy here, etc. Yeah? But there is a possibility that there are elements in W1 which are not in W4, just like this part here. Okay? And etc. But the main point here is if you get their intersection, all of them, it becomes a subspace. Okay? I think I have Melissa first. Yes, Melissa?
So the intersect of zero is a subspace within a subspace?
What do you mean intersect of a zero? Zero is just an object.
Okay, so zero is just an object and all of these W subspaces overlap it.
Yep,
The area that it is overlapped is called
a
a,
subspace.
a
It's a
subspace.
subspace. It's the intersection.
So it's called an intersection. We
Yeah.
just we don't like, because I'm getting confused when you say like this, like it's a subspace within. It sounds like it's a subspace within a subspace, but it's
This
a
one is a
subspace.
subspace within a subspace. This is,
Okay.
in fact, all the intersections is a subspace within other subspaces, right? These
Okay.
intersections is inside W1 also, double
Okay.
inside W4 also, etc.
Oh, okay.
Huh?
So the intersection is within multiple subspaces.
Yes, it could be within the multiple subspaces. In fact, if you have defined your subspaces, okay, it must be inside those
Okay.
multiple subspaces.
Okay.
Okay.
Thank you.
Yep. Other
Yeah,
question? Yeah.
yeah,
Yes.
it's clear to me now. Like what I was trying to verify was that since the region, the
Okay.
intersecting region is part of the four subspaces,
Yes.
then the region should be a subspace of the subspace, and it should hold
Yes.
true. It should hold true for the conditions. Oh, like it's a part of the object of the subspaces,
Uh-huh.
but yeah, but I realized that they're all part of the larger subspace V
Yes.
of the vector space.
Yes.
So
That is true. Yeah.
yeah, I think that part was where I got confused, but I get it. Yeah.
Okay. Okay. That's good. Okay. Let me show the quick proof for this. Let me show the quick proof for this. Okay. So we define. So proof, let W be equal to the intersection. W1 intersection W2 intersection until WR. So you do all the intersections, right? Okay. So let U and V be elements in W. So you get two elements in the intersection. Okay? Then this means then U and V are in all of W1, W2 until WR, right? Since you get your U and V to be in the intersection, then this U and V, they are in all of W1 until WR. Okay? Since W1 until WR are all subspaces, okay? So U plus V is also in all of, all is in all of W1, W2, WR because they are all subspaces. And therefore, therefore, U plus V is in the intersection. That's your first statement in the subspace test. You get two elements in the set, you show that the sum is also in the set. So U and V is in the intersection W1, W2 until WR. Then U and B must be inside of all W1 until WR. Now, W1 and until WR are subspaces. You add them, you add U plus V, they must be, or it must be inside all of W1 until WR because again, W1 until WR are subspaces. So if U plus V is inside all of this, it is inside the intersection, which is W. Okay? Also, for any scalar k, the scalar multiplication ku is in all of W1 until WR. And again, the reason is W1 until WR are subspaces. So, KU is also in W. Therefore, W is a subspace. Is a subspace. Yeah? That's the short proof for this. You know, you know that the intersection W1, W2 until WR contains elements which are in all of W1, W2, and WR. Okay? So we get this. We get this picture here. We get an element somewhere here in the shade, the red shade here. Then the element is contained in all of this W1 until W4. You get two elements. If you add them, the sum will be inside W1, will be inside W4, will be inside W3, will be inside W2. And therefore, inside the red shade here. Okay? So that's your first statement. And also for the second statement, similar illustration. Okay? Now, another construction. Suppose we get a V1, V2 until VR be a non-empty set of vectors in a vector space V. We consider set W to be the all possible linear combinations of vectors in S. Okay? So what is this? So let me write S or the W here. W here. These are all possible linear combinations. So you have S1 V1 plus S2 V2 plus until you have SR VR. Here, linear combination. So S1, S2 until SR. These are all scalars, are scalars. So this is your set W. All possible linear combinations of vectors. S1, S2 until SR, they can be zero. So that's a possible linear combination. 0 V1 plus 0 V2 plus until 0 VR. And that's just your zero vector. Okay? That's just your zero vector. So if we collect this, this set here or these elements here, put it in a single set, okay? Then this W is a subspace of V. Take note, S and V, they are different. Okay? S is just the collection, V1, V2 until VR. W here, sorry, I think I said S and V are different. S and W are different. S, collection of vectors, V1, V2, and VR until VR. While W, possible linear combination. So S is inside W. Okay? S is inside W, but there's more. There's more. Okay? So if you collect that using the same operations as V, W is a vector, is a subspace of V. Okay? And there is a special name to this set. Okay? The set W above, this is called the smallest subspace of V that contains all vectors in S. Okay? It's the smallest subspace. Take note of that. Subspace of V that contains all the vectors in S. This means if we have other subspaces of V, okay, that contains all the vectors in S, okay, then that that subspace must contain W. Okay? So what is that? You have your vector space V here. Then you have your V1, V2. Let me write V3. This is your S. This is your S. Just the three of them. S. Your W will be much bigger. This is your W, and this is a subspace. Subspace. It's the smallest subspace. Okay? If you try to find another subspace that contains this S, V1, V2 until V3, okay, that subspace must also contain W. So this subspace here, subspace bigger than W, bigger than W. Okay? If you try to get a collection, say this guy here, this purple here, this purple here contains S, but this purple here is inside W. Okay? It is smaller than W. This here cannot be subspace. Okay? That's what this remark tells us. W is the smallest subspace of V that contains all of the vectors in S. If you found another subspace of V that contains the elements in S, that subspace must be bigger than W. Okay? Example. Let V be the vector space, the three-dimensional real space. Let R3 be the vector space of ordered triple of real numbers with the usual addition and scalar multiplication of vectors in R3. Let us consider this S. The S contains these two ordered triples. 2, 1, 4, negative 1, 2, 2. Okay? Then we collect W, all possible scalar or all possible linear combinations of W. Sorry, this one should be 4 here. This one should be 4 here. This one should be 4. Okay? So the theorem tells us this W is a subspace of V. Okay? It's a subspace of V. Okay? So meaning all of these combinations. If we look at this graphically, we can think of 214 as a vector. Okay? We can think of 214 as a vector that looks like this. And then negative 1, 2, 2 as another vector that looks like this. Okay? The plane, okay, the plane parallel to both the two vectors here, okay, it's a vector space. Okay? And it is a subspace of your R3. Okay? And we can prove this. We can prove this, that it is a subspace. So how? Again, we just use those two. We just need to show the two conditions. Okay? So um, let U be equal to K1, K1, 214, 214 plus M1, negative 1, 2, 2, and then V, K2, 214 plus M2, negative 1, 2, 2. Then if you add them, then U plus V, this is simply, of course, 214 is the same as this, so you can just add these two scalars. 2 K1 plus K2, 214. Then the other one, same, M1 plus M2, negative 1, 2, 2, negative 1, 2, 2. But note, this guy here, just another scalar. Another scalar. And also this guy here. It's just another scalar. And therefore, it's inside this, W. KMM are scalars. K1 plus K2, it's just another scalar. M1 plus M2 is just another scalar. So this is inside W. Similarly, you have L, U. This is just L, K1, 214 plus L, K, M1, negative 1, 2, 2. And again, LK1 and LM1, they are just another scalars. So they are both in W. This is in W. And that's it. W is a subspace of V. And this is how you prove it, to prove the general theorem here. That's how you prove it. Possible linear combinations. Okay? Question. Now, this kind of situation, getting all possible linear combinations, as I have said earlier, it's a special subspace and it has a name. Okay? So let S be the set of vectors v1, v2 until vr. So non-empty set of vectors in a vector space V. Then the subspace W of V consisting of all possible linear combinations of the vectors in S. We call that the subspace of V generated by S. Okay? So we call that W, okay, the subspace of V generated by S, and we say that the vectors v1, v2 until vr span W. Okay? And we denote this subspace W as span S, or span of v1, v2 until vr. So the span of a set, okay, the span of a set generates a set, a bigger set. Span of objects, v1, v2 until vr, it will generate another set. and that set becomes a subspace. Okay? So for example, in the previous example, W, okay, W can be written as the span of the vectors 2, 1, 4, comma, negative 1, 2, 2. Okay? And that span, again, this guy here, this should be 4. Okay? So that span can be written this way. K times 2, 1, 4 plus M times negative 1, 2, 2, where K and M are scalars. So the spanning set. Okay? Okay? Another example. Let me just add it here. Another example here. If you get the span of the vector 1, 0, 0, comma, 0, 1, 0, comma, 0, 0, 1. If you get the span of this will give you R3. Okay? So the span of this vector will give you the three-dimensional space, R3. Okay? Now, what else? Let us go back to linear system. We get the solution set of a homogeneous linear system. Okay? So the solution set of a homogeneous linear system AX equals 0 of M equations in N unknowns. Okay? It is a subspace of Rn. Okay? It is a subspace of Rn. We call that the solution space. We call that solution space. So let W be the solution space. The solution space of AX equals 0. Homogeneous, take note of that. So let us prove that this W is actually a subspace of Rn. Okay? And to do that, we use the two statements that we know, that we need to prove. Let x1, x2 be in W. We want to show that x1 plus x2 is also in W. But we have been doing this. We have been doing this. Then ax1 equals 0. ax2, this is also 0. Right? Because x1, x2 are inside the solution space. Okay? The solution space. So they must solve this equation. So ax1 equals 0, ax2 equals 0. And ax1 plus x2, okay, this is equal to ax1 plus ax2. This is equal to 0 because you have ax1 equals 0, ax2 equals 0. So what does this mean? So x1 plus x2 is also a solution of this and therefore must be inside W. Because x1 plus x2 solves the equation ax equals 0. from here. So this is your first statement. The second statement, let k be any scalar, then what do we have? A, kx1, okay? But this is simply k, ax1, right? You can factor out the scalar k outside the matrices. But this is again 0 because ax1 equals 0. So k times the 0 vector, it's just the 0 vector. And so kx1 is also a solution and therefore inside W. So W is a subspace. Subspace of Rn. We did not say that x1 is a vector in Rn, but it must be a vector in Rn because W is a solution space of this. And the right hand and the x here has n numbers, n unknowns. You see that? N unknowns. So x1 and x2 contains n entries. Okay? So they are all in Rn. So this is the proof of this one. The solution space is actually a subspace. Okay? And this is only true for homogeneous linear equation. Remember that. This is only true for the homogeneous linear equation. If you have the non-homogeneous system, okay? If you have the non-homogeneous system, it may be false. In fact, it is false if your right-hand side is not the 0 vector. Okay? So example, find the solution space of the following linear system. Then give a geometric description of the solution space. Look at this. Okay? We can solve this. We can solve this. Okay? But let us see. Notice 1, negative 2, 3. Second row, 2, negative 4, 6. Third row, 3, negative 6, 9. Okay? 3, negative 6, 9. As an equation, as a linear system of equations, this is just what? X1 minus 2x2 plus 3x3 equals 0. Okay? And then you have 2x1 minus 4x2 plus 9x3 equals 0. And then the other guy, it's 3x1 minus 6x2 plus, sorry, for the second part, this is 6 here. And this is the 9x3 equals 0. But these are all equivalent equations. Okay, these are all equivalent equations. This will only give us x1 minus 2x2 plus 3x3 equals 0. Okay? So what is the solution space? So here we can let x2 equals t, x3 equals s, then x1 equals what? 2t minus 3s, 3s, right? So the solution, the general solution is, the vector of the form 2t minus 3s, comma, t, comma, s, right? But this is the same as t times 2, 1, 0 plus s times negative 3, 0, 1. You get this? So t times 2, that's your 2t there. Second component, you have t times 1, that's your t there. Third component, t times 0, that's 0. So there's no t on the third component here. For this part here, you have s times negative 3, that's why you have the minus 3 there. S times 0, there is no s on the second component. S times 1, that's your s. Okay, so this is the general solution. Okay, so what is the solution space? Solution space is, take note, t and s here, they are all scalars. They are both scalars. So the solution space is the span of 2, 1, 0 and negative 3, 0, 1. Okay? Span of this. That's your solution space. Geometrically, you have two vectors. Okay? And for the two vectors, look at this. This is like a vector equation of a plane. Remember your vector equation of a plane? You consider 2, 1, 0 as one vector and negative 3, 0, 1 as another vector. T and S are scalars. So this is like an equation for the plane. So geometrically, the solution space is just a plane. Yes, question.
Yeah. So after you wrote the solutions on the top, for the homogeneous system, the reason why we only took out the first row is because they're all equivalent lines.
Yes. If you
Equivalent equations.
multiply 2 on the first row, you will get your second equation. If you multiply 3 on the first row, you get your third equation.
Would
So
that
they are all the same.
would
They
that
are all,
always be the case?
not really, depending on
No.
your matrix here. Depending on your matrix.
So, if that's not the case, then we would need to write
You
uh
will try to solve it as if like similar to what we did in the first chapter.
hmm.
It's the same. You will still have to find the general solution. So it will be something like this. Or possibly the general solution is just the zero vector.
Yeah.
Yeah. For example. So again, as I have said, the geometric interpretation of this is just a plane. Okay, this is a plane. Let us look at this. First row, 1, negative 2, 3. Third row, negative 2, 4, negative 6. So very much similar to first row, right? This second row, they are different. 1, negative 2, 3, negative 3, 7, negative 8, negative 2, 4, negative 6. Okay? So this guy here, okay? This guy here will be similar to the linear system. X1 minus 2x2 plus 3x3 equals 0, and negative 3 x1 plus 7 x2 minus 8 x3 equals 0. And I can leave out the third equation. So the third equation is similar to this. Okay? Yeah, let me write that. Negative 2x1 plus 4x2 minus 6x3 equals 0. But as I have said, we'll just have to work on the first two equation here. First two equations here, because third equation is similar to first equation. Okay? So the question is, how do we solve this system? How do we solve the system? You can do what? Gauss-Jordan elimination. If you are going to look at this matrix here, you can do that. Okay? You can find the RREF of that using Gauss-Jordan elimination. Yeah, maybe let us try that to practice. Let us recall that Gauss-Jordan elimination or the RREF. So you have 1, negative 2, 3, negative 3, 7, negative 8, negative 2, 4, negative 6. So what we can do here is to replace R3 plus 2R1. Yeah, replace R3 plus 2R1. So the third row becomes 0. Everything will be 0. Negative 3, 7, negative 8. Third row will be 0. Okay? And then we now replace R2. We add 3R1. 3R1. So R1 is the same. 1, negative 2, 3. 3R1 plus R2. So minus 3 plus 3, this becomes 0. 7 minus 6. Oh, that's nice. That becomes 1. 7 minus 6. And then minus 8 plus 9. Plus 9. So that's again 1. Then here we have 0, 0, 0. And finally here, to find the RREF, we replace R1 by R1 plus 2, R2. We do this. So 1 minus 1 plus 0, that's 1. Minus 2 plus 2, that's 0. 3 plus 2, that's 5. Check my arithmetic here. And then we'll have 0, 1, 1, 0, 0, 0. So this is the RREF. Okay? The RREF. So what we can do? We let x3 equals t. Sorry, x3 equals t. Then x1 plus 5x3 equals 0. x2 plus x3 equals 0 implies that x1 equals negative 5x3, but we label that as t, and x2 will be negative t. Okay? So the general solution is this. The general solution is of the form negative 5t, comma negative t, comma positive t, or simply this is just t times negative 5, negative 1, positive 1. Okay? So the solution space is the span of that vector, negative 5, negative 1, positive 1. Okay? And what is this? What is this equation here? You have a vector, negative 5, 1, negative 1, 1. You multiply any scalar, either it just elongates or go to the other direction. Okay? So this is just a line. Geometrically, this is a line. Geometrically, a line. Okay? Let me go back to the previous here. Let me just write geometrically a plane. Geometrically a plane. Okay? Question. Okay? One last example here for this set. Find the solution space of the following linear system, then give a geometric description of the solution space. And look at this. 1, negative 2, 3, negative 3, 7, negative 8, 4, 1, 2. Okay? Solution, you can do your RREF. Okay? But in here, what I'm going to do is to find the determinant of that. So determinant of that matrix, 1, negative 2, 3, negative 3, 7, negative 8, 4, 1, 2. I want to show that the determinant is not equal to 0. Because if that's the case, this matrix is invertible. Okay? And if the determinant is not equal to 0, this has a unique solution. Okay? And the only solution that we can find here will be the 0 vector, if the determinant is not equal to 0. So that's why I'm going to work on that method. Negative 1, 1, negative 2, 3, negative 3, 7, negative 8, 4, 1, 2. Okay? Then we augment 1, negative 3, 4, negative 2, 7, 1. Okay? So we have this, and we have this. Let us compute. This is 14. Negative 2 times 4, that's negative 8. Negative 8 times negative 8, that's 64. 3, negative 3. 3, negative 3, that's negative 9. And then the going up. So 4 times 7 times 3, this is 84. 1, negative 8, 1, that's negative 8. 2, negative 3, negative 2, that's positive 12. Check my multiplication, please. So the determinant, it's 14 plus 64 minus 9 minus quantity 84 minus 8 plus 12. What is this? Check, it's negative 19. Okay? Negative 19. Try to verify this. But what does this mean? Determinant is non-zero. Okay? Determinant is non-zero since determinant is not zero, the system has a unique solution. And that solution is the zero vector. Is the zero vector. So the solution space contains the point. The solution space is the zero vector space. So this is just 0, 0, 0. Okay? And this is just a point. Okay? So geometrically, it's a point. Okay? Question. So in these three equations in three unknowns, okay, for the homogeneous linear system, there are three possible solution spaces. Either the point, which is this, a line similar to this, or a plane similar to this. And these guys here, according to this theorem, they are all subspaces of your R3. Okay? One final remark in here. Suppose we get two sets of vectors. Okay? S equals V1 until VR. S prime, let us call it W1 until WS. S and R, they may not be the same. Okay? S and R, they may not be the same. This S, this R here, and then this small s here, they may not be the same. Meaning the number of elements in S may not be the same as the number of elements in S prime. Okay? So let S and S prime be non-empty subsets of vectors, okay, in a vector space V. Then the span of S equals the span of S prime. Okay, take note, span of S equals the span of S prime if and only if each vector in S is a linear combination of those in S prime, and each vector in S prime is a linear combination of those in S. Okay, so span of S equals span of S prime implies all the vectors in S are linear combinations of those in S prime, and all the vectors in X prime is a linear combination of those in S. Conversely, if all the elements in S are linear combinations of elements in S prime, and all the elements of S prime are linear combinations of S, then they have the same span. Okay? Okay? Just to see this statement here. For example, the span of 1, 0, 0, 0, 1, 0, 0, 0, 1. As I have said, this is your R3. Okay? This is your R3. Now, I can look also at the span of 1, 1, 0, 0, 1, 1, 1, 0, 1. Okay? I can look at the span of this. This is also equal to R3. Okay? Furthermore, I can also look at the span of 1, 1, 0, 0, 1, 1, 1, 0, 1, and then maybe 1, 2, 1. If I look at the span of this, okay, this is also R3. So, I have three vectors, 0, 1. I have three vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. I get the span of that. I get the three-dimensional space R3. I also get another set of vectors, 1, 1, 0, 0, 1, 1, 1, 0, 1. If I get the span of this, I will still get R3, meaning these two spans are the same. Okay? In addition, suppose I have already these three vectors and I added another vector, 1, 2, 1. Okay? I get the span of this, okay? That's still R3. Okay? So what does this mean? If I get the linear combination of all of this, okay? For example, 1, 0, 0, I can write it as a linear combination of any of these three vectors here. 0, 1, 0, I can also write it as a linear combination of these three vectors here. 0, 0, 1, I can also write it as a linear combination of these three vectors. That's your first part here. Conversely, 1, 1, 0, I can write it as a linear combination of any of the three vectors above here. 0, 1, 1, also a linear combination of the three vectors here. 1, 0, 1, a linear combination of these three vectors here. That's the second part here. Okay? And that's why they have the same span. You can also do that, this span here with the first part here, or this, and etc. Okay? For example, further example for this. Let us label this as our S. This is our S. This is our S prime. This is our S double prime. Okay? Your 1, 1, 0, 1, 1, 0, you can write this as 1, 0, 0 plus 0, 1, 0. Okay? So I just use two elements in this here. Your 0, 1, 1. This is equal to 0, 1, 0 plus 0, 0, 1. And finally, 0, sorry, it's 1, 0, 1. I can write this as 1, 0, 0 plus 0, 0, 1. So each element of S prime is a linear combination of elements in S. Okay? Now, can we write each element of S as a linear combination of this here? Okay? This here. So how do we do this? Let me give you an example. 1, 0, 0. This is equal to. This is equal to 1 half 1, 1, 0 plus this 1 half, or I should have 3 halves. Let me just write this 1 half 1, 0, 1. Yep, minus 0, 1, 1. See that? 1 half times 1, that's 1 half, 1 half times 1 here. So that's your 1. This is 0, minus 0, that's your 1. The middle component, 1 half times 1. Wait, 1 half times 1. That's 1 half plus 1 half. This is 0. Yeah, I think this is minus 1 half. There is a minus 1 half here. So let me adjust this. So minus 1 half, 0, 1, 1. Okay? So 1 half plus 1 half plus 0, that's 0. 1 half plus 0 minus 1 half, that's 0. 1, this is 0, plus 1 half minus 1 half, that's 0. Yep. So 1, 0, 0. This element here can be written as a linear combination of the 3 elements here. Same is true with this guy. You can write it as a linear combination of these 3 elements. And this guy, linear combination of these 3 elements. Okay? So since we can do that, okay, then they have the same span. Span of this equals span of this. In fact, yes, R3, R3. Okay? You can do that here, the same thing in S double prime. Continue, try to find, I'll just put it here, try to find the linear combination for this and the linear combination for this using the elements 1, 1, 0, 0, 1, 1, and 1, 0, 1. And you can therefore conclude that they have the same span.